Hey guys, welcome to the lesson 13 group video. We're going to start with number 1. We are using the Sanger method to determine the nucleotide sequence of the DNA molecule shown below, in this case above, as it's written up there. So question A is asking us what would the banding pattern look like on the gel. And so we have made a diagram of our electrophoresis gel with each lane for the ATPs. So DDGTP, ATP, T's, and C's right there. And our banding pattern corresponds to the, what do we call it, the complementary strand of our DNA supersequence up here. So at the very bottom, we're going to start and have it's just going to be the corresponding base to each of these. So CTG, we're going to go at C for the lowest band, a T, followed by a G, followed by another C, corresponding here, with an A, then 2 T's, as we're kind of ascending our electrophoresis. We're going to be followed by 2 G's over here, there. Jump 1 lane over to an A, all the way over here to a C that corresponds to that leucine, followed by, oh, I missed that T. I'm indeed missing a T. There is the next band will correspond to that thymine, and the A will be our very last nucleotide. So banding pattern is kind of zigzaggy, and we'll go generically like that, but it's listed over here on my left side of the screen, that side. Part B asks us, suppose I use E. coli DNA polymerase 1 during the sequencing reaction of instead of Taq polymerase. So what happens if we use not the heat-resistant polymerase? Well, it's going to denature. It's hot enough between 70 and 90 Celsius that the normal E. coli polymerase will denature and will not function. Part C, if we accidentally add E. coli DNA helicase, that's not really going to affect the reaction because PCR, whether via traditional PCR or the Sanger method, does not use helicase to separate the DNA. Rather, it's separated by heat. So the heat is going to denature the helicase, and it's just going to float in solution, doing nothing. Part D says, suppose I add a DD-ATP to one of the 4 tubes, but you forget to add the rest of the double deoxy nucleotides, assuming all other components used for sequencing are normal. So the only one of these that we're going to have is the DD-ATP. Everything else will just have the one heavy band at the one end because the whole DNA sequence was normal. And then we'll have these 3 bands of the DD-ATP. And that will do it for question 1.
For question 2, we'll just fill in the blanks here. During a typical PCR cycle, the synthesis step is done at 72C. That's where the Taq polymerase works best. While the annealing step is done at 55 degrees Celsius. The annealing step is when the primer attaches onto the DNA strand. B, AMP resistance is the common selectable marker found in many plasmid vectors that when bacteria has taken up the AMP resistance gene, it can survive on plates that have ampicillin on them, which is useful for research. And recognition enzymes are what recognize and cleave DNA molecules at palindromic sites. You need to cleave that in order to insert vectors or inserts into your vector. C, during agarose gel electrophoresis, DNA is placed in an electrical field. DNA microexposed to the positive electrode during electrophoresis. This is because DNA is negatively charged along the backbone, so it's attracted to a positive electrode. DD-ATP lacks both the 2' and the 3' OH group. That's what makes it unreactive, so that you can't build onto it with the polymerase. So wherever DD-NTP lands, your strand will end there. E, transformation is the term used to describe the process where bacteria take the DNA molecules from the environment. That can be done multiple ways. Heat shock or electrocuted are very common though. F, during blue-white screening, IPTG is commonly used to induce the expression of the operon. IPTG acts similar to lactase in that respect, or lactose, excuse me. Well, X-gal is cleaved by beta-galactosidase to turn E. coli cells blue.
So, question 3 is saying we're using PCR to amplify the region of a double-stranded DNA fragment of E. coli. The sequence to be copied is located between the sequences in bold below. On your paper, I didn't draw up the whole sequence, but my primers are going to be right here and right here. Remember, DNA is synthesized in the E3-5 direction. If we were to switch these and put a primer down here and up here, it would synthesize out instead of in, so that's not quite what we want. My first primer on the top right should read UCGGA, UU, AA, CGU, DAG from 3 to 5 prime. Second primer over on the left side of the screen is a 5 prime GAG, CC, UU, CA, CUCA, GUG, 3 prime. Now let's do a little bit of math for question B with our equation. The temperature in Celsius is equal to 81.5 plus 0.41 times the percent GC, percent 1 cytosine. And in the case of this first primer up here, there are 16 total bases, 8 of those are G or C, so we're going to call this 50% minus 675 over N, is just the total number of nucleotides, and that was 16, using my parentheses, and that I got was equal to 59.8 degrees Celsius. Among friends, we'll call that 60 C. Same equation for this second strand, T sub C equals 81.5 plus 0.41. In this case, they're the same 16 total nucleotides, but 9 of them, instead of 8, are G's and C's. Therefore, we have a different percentage, and that works out to be 56.25 minus 675 over the same 16. Plug that in your calculator. My temperature in Celsius was equal to 62.4, if you will. And we can run in that case 62 out of it. 62 degrees Celsius. Okay, so that was part B. Part C says, what are the sequences of the 2 newly synthesized strands if DD-CTP is accidentally induced? Okay, well then, we are going to then synthesize DNA. Clear up some real estate, if you would. We've got my primers done out of the way. Let's see up here. The top strand of DNA, 3-5 direction, okay. And this part of the problem, sorry I did not write it, I'm going to show you again. We're going to find the corresponding nucleotides to this first list of DNA nucleotides up to that X on that first C, because we have the DD-CTP. So for the top polymerase and the bottom, wasn't organized the best, sorry about that. So we'll go 3 prime, CT, AA, triple T, 5 prime. So you're going to synthesize your DNA on the top strand only until the C because of the DD-CTP. That lacks the 3 prime hydroxyl group, can't form a bond. So you're going to hit the C and then stop. On the bottom, we're going to go a little bit further. G, 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 A, T, T, A, G, and same case, we hit C, and that's it. You cannot synthesize beyond that. And so those are my 2 sequences of DNA that I will get given these primers. Question D says, why are DNA A and the DAM methylase proteins not included in PCR. Well, DNA A is just an initiator in replication, acts on the ORIC of the bacteria, and that isn't the case here. We denature our DNA via heat instead of a helicase or the point of origin. The DAM methylase inactivates the ORIC just so replication doesn't keep going faster than the cell can divide. But again, since we denature our DNA via heat, we don't need either DNA A or the DAM methylase. So that does it for number 3.
For number 4, I'll start by drawing our gel here that we're going to visualize. Sorry, it's kind of hard to see. So there's 7 lanes in the gel here. The first one has the marker in it, and the marker has different lengths of DNA, just standard lengths that we can use to measure all of our other DNA off of. So we'll have one at 1,000, 500, 400, 300, 200, and 100. Remember that we have larger at the top because they move slow and small at the bottom because they move quickly. Our first lane was just digested with BAMI. So if we just read the DNA fragments produced, it has one at 50 down here, one at 350, and one at 500. 2 just has E. coli, which is 200 and 700. Lane 3 just has Hindi 3, which has a band at 300 and a band at 600, just below that 700 mark. Lane 4 has fragments that are 50 base pairs long, 150, 200, and 500. Lane 5 has, again, a 50, a 100, a 250, and a 500. And then lane 6 has a 100, a 200, and a 600. So you just draw a band that roughly corresponds to wherever the bands on your marker lie. So we should have a gel that looks like this. For B, we need to draw the linear restriction map that indicates the location of the restriction enzyme sites along the hypothetical DNA molecule. So I'll erase this really quickly so that we can do that. So if we add the base pairs in each section, we'll find that our whole DNA molecule should be 9,000 base pairs long, or 900, excuse me, base pairs long. If we first just look at when we have BAMI, we'll notice we have 3 fragments, so that means we have 2 BAMI sites. One's at 50, so I'll mark about 50 right here. And the other one's going to be, give us a fragment of 350 and 500. So we'll just guess and say that we have another one at 400 base pairs, which gives us a fragment of 50, 350, and then 500. And we'll just see if that works as we go forward with the other ones. E. coli gives us fragments of 200 and 700 when it's by itself, So I'll just mark a little site here at 200, and that will give us a fragment of 200 and 700. So let's see if these match up when we have the BAMI and E-Quarry together. That's lane 4. We should have a fragment that's 50 base pairs long, one that's 150, which fits perfectly between the 50 and 200 here, another that's 200, we see that right here between 200 and 400, then final one of 500. So we're pretty comfortable here having our 2 BAMI sites right here and the E-Quarry site right here. Finally, we need to figure out what the Hindi 3 is. So that has a cut site, and I'll have 2 fragments of 300 and 600. So maybe we'll get lucky. We'll try putting it right here at 300 and see what we get. So if it's in the right spot, this should create the same, we should be able to figure out what fragments we ought to have. So let's look at when we have ND3 and E-Quarry, what we should have. So if we look at our reaction 6, that has ND3 and E-Quarry, we should have a fragment that's 100 base pairs long. That fits right here between 2 and 300. We should have one that's 200 long. That fits right here between 0 and 200. One that's 600 long, between 3 and 900. And if you check the other reactions, everything all checks out. So this is what our restriction enzyme match looks like. For problem C, it just asks us if we use all 3 restriction enzymes, what length of fragments are we going to get? So we just see how far it is between each restriction enzyme. It's 50 base pairs right here. Then between 50 and 100 is 150 base pairs. Between 2 and 300 and 3 and 400, they're both 100 base pairs. So we'll probably have a thicker looking band around 100 base pairs. And finally, we'll have the 500 base pair stretch.
So question 5, we are interested in studying our YFG, your favorite gene, and we're identifying this in the yeast Saccharomyces cerevisiae. We just need to outline the steps to then generate the cDNA, clone it into a plasmid, and then use the blue-white screening. So the first step is we need to take the mature mRNA transcript from the Saccharomyces yeast, mix it with the poly-DT primer that corresponds to the poly-A tail. Once that's mixed, you then add reverse transcriptase to synthesize the DNA, and you need all 4 DNTPs, so you have the appropriate nucleotides to add. The reverse transcriptase will synthesize the complementary DNA strand to the mRNA, at which point we will add RNase H that degrades and digests the mRNA, primer, everything, and leaves just the newly synthesized DNA. The final step in the generation of cDNA is to add the DNA polymerase 1 from E. coli to then synthesize the second DNA strand and give you a double-stranded DNA.
Now that we have our double-stranded DNA, we just run a PCR reaction to multiply. We're going to need multiple copies. So we'll just design some primers that match this DNA sequence. And we'll use primers that have restriction enzyme sites on them so that we can digest this later. So we'll throw the primers, syntactic polymerase, our double-stranded DNA, the strand, along with the buffer solution all together. And we'll put it through the heat cycles until we multiply our DNA strand like crazy. And then we'll put it through a digestion phase where we'll use whatever restriction enzymes we planned. We'll mix that with our PCR product as well as the vectors, whatever vector we use. And what's important about the vector is that it has a restriction site right in the middle of the LAC-Z sequence. So once we've digested those, we'll mix them together, and the insert will be inserted into the vectors to transform our recombinant DNA into a bacteria, E. coli, for example. And then we'll grow it in an LB broth and culture it on a plate that has IPTG and XGAL. So with IPTG and XGAL, if the bacteria has an operating LAC-Z gene between the XGAL and the IPTG, it will turn blue. So we'll be able to tell that if any bacteria turns blue, that means we didn't disrupt the LAC-Z gene like we hoped to, and they don't have a recombinant DNA. However, if a bacteria does have the recombinant DNA, that means its LAC-Z is inoperative, and so it would be white. Thanks for coming this week, and have a good finals week and good 7-week break.